All right, in this video I'm going to be talking about volume in the double integral sense. So what we're going to do here is we're going to start with the idea of the Riemann sum, right? Suppose you've got z equals f of x and y, which is giving you some sort of surface in space, right? And maybe I will draw that, kind of like that. Just kind of envision it being kind of a nice little dome or something. Nothing too complicated. And it's above some sort of like region in the plane. And we want to know the amount of volume above this region R, right? And underneath the surface. What we're going to do is we're going to start with the idea of Riemann sum. Now, when we were looking at area in the single variable case, what we did was we took, an area, and we were going to cut it up into little tiny rectangles. Okay? Now, rectangle, two-dimensional object. I need a small three-dimensional object. So really, it's going to be a rectangular prism is what it's going to be. I prefer to think of it as like, I don't know, like a really skinny twig or a dowel rod or something. Very, very narrow, but as tall as the function is. And I'm going to just draw you one of these, right? Goes up to, say it's, hitting the surface right there, and it's tracing back to there. Okay, now this is a thing, and it's got some thickness, right? If I was to, well, I'm not going to try to draw it three-dimensionally, that's a bad idea. But what I'm going to tell you is that, in terms of this height is z, right? This is f of x and y. And then, it's got a base, right? It's a prism. This is a very poor drawing. But it's got a base, and the area of the base is, well, very small, right? That's the idea. It's delta A. So this really tiny stick of volume, which I might call delta volume, is going to be, well, the way you find the volume of a prism is you take the area of the base and you multiply it up by the height. So it's delta A times f of x and y. Or, as you might expect, I'm going to write that as f of x and y times delta A. And in order to get all of the volumes, I'm going to have to add up all the small pieces of volume. Sum of delta B, which in the limiting case is going to go towards volume equaling, the integral of f of x and y dA on R. Now we know because we're taking the integral dA, this is actually a double integral. Okay? So just in general, right, just saying I'm adding them all up to turn it into an integral, and then the kind of the fact that I'm going to be going off of for the rest of this video, I'll put up here, right where I put the thing for area, is that volume is going to be the double integral over some region of f of x and y dA. Okay, so this is where we're going to mix in an integrand. Okay, before we were just integrating one. And later on, when we start talking about triple integrals, we might be interested in integrating dV, just to find the volume of something. And that's, we'll get to that. Okay, so, at this point, now that I've got the idea of volume as a Riemann sum, I do probably need to define it. That would probably be best practice for this class. Throw out all of the definitions. Okay, so the double integral over R of some function dA is given by, just like before, the limit of a Riemann sum. Okay, this is going to be the limit of the sum as I runs from 1 up to n. I'm just going to add up all these small pieces of volume, these little sticks. Okay, these sticks have volume given by f of x and y times delta A. Now, if we're going to split it up into a bunch of different sticks, it's going to be f of each individual xi and yi, which is kind of a whole, you don't really want to go into the process of computing these Riemann sums, and especially not the limit of these Riemann sums, I promise you that. So what we're going to do instead is we're just going to say, f of each x and y as you run over the course of your R in some systematic way times delta area. But, can't guarantee that I'm going to cut this thing up regularly and that each delta area is going to have the same area. So, each delta area, each respective one. And I'm going to take the limit of this as the norm of my partition goes towards 0. Okay? And just to remind you what that means, the partition is, you know, how I'm going to cut up R, or how earlier I was going to cut up my region that I was going to integrate to find area under in the single variable. And the norm of the partition in single variable was the width of the widest rectangle. Now in this case, it will be the area of the largest piece of area that we're going to use our Riemann sum on. Okay? And so that's the definition of the double integral. And it's the limit of the Riemann sum, and that's for this class, that's pretty much all you need to remember. Just like before. Now, what am I interested in doing? Oh, okay, I'm going to compute one of these volume double integrals, just again for the practice, and then I'm going to come in and draw the pictures and show you what it means. All right, so if I, you know, for instance, had some function, and I wanted to integrate it over some region that was given to me, I'm going to show you how to do that. And then I'm going to show you what it means and what we're actually doing here when we're double integrating after that with some drawings. So, I'm going to say, all right, I need to kind of get an expression for R to make this happen. This is kind of both vertically and horizontally simple, but I don't have an equation for this thing, and I tend to default to y equals, right? And so what I'm going to do is I'm going to say I'm going to let y run from 0 up to the y equals equation of this line. So I'm going to do dy first, and then dx. Okay. This is, I think, 1 minus half of x, yeah. And then dx, or x is running from 0 to 2. And then I put in my integrand. I didn't really leave enough room, but 2 minus x minus 2y. Almost certain that's not large enough to clearly make out on screen, but that's all right. Okay, this is the type of thing we're going to be able to do. I think, again, this is the type of thing that you need to practice, so you should pause the video. I'm going to work it while it's paused, and then I will resume recording in a second. All right, there you go. After a little bit of work, you see that the volume is going to be equal to 2/3. Okay. Now, you're like, okay, I'm getting to the point where I can just kind of compute these. I can go through the steps. It's like, what am I actually doing here? And so I think that this is a really good one. Point out, this is a plane. This is an equation of a plane, right? Linear in x and y is going to make you a plane. And a plane, it's going to kind of downslope towards positive x and positive y. And so it's going to make it tetrahedral. And I can draw you a picture of this. I'm going to switch the orientation of my usual XYZ plot so that we're looking right at the positive x and y axes. So what I'm going to do is I need this one to go. Let me just make sure I'm going to draw it right. Yeah, I need more x than y. So I'm going to go over here. That's going to be my x-axis. That's going to be my y-axis. Let this be my z-axis. And I'm afraid that with the types of drawings I'm going to do, I'm going to use that whole bottom board for this because I don't want to go too short. All right, so I'm going to say that's going to be my x, that's going to be my y, and this will be my z. All right, and so this is the type of plane, and if you just look at its intercepts, it's pretty easy to understand what's happening here. It's going to have intercepts at x equals 2, y equals 1, and z equals 2. So, doesn't have to be exact. I just need it big enough that I can draw on it. Okay, so I'm going to go over here, and I'm going to connect these. Please be a good one. Oh, that looks nice. And then one down here. And here also. All right. And you know, if I was to shade over it, you would probably be able to see it better. But you can see that this is a tetrahedron. Okay, and what I'm proposing that we're doing is that first, or just in general, what we're going to do, this should be kind of familiar from AP Calculus. We did this type of thing, you know, for a while. So I've got, you know, maybe make sure that's parallel. That. I've got myself a little pink triangle here. I really want it to be solid to give you that perspective. Okay, that looks pretty nice to me. Okay, what's going to happen is this area of the pink triangle is something that we can add up as x runs from 0 to 2. And what do you want to bet? That the area of that pink triangle is given by 1/4 x squared minus x plus 1. So really that's what we're doing. Okay, just kind of give you the idea, is that when we integrate the first time, what we're doing is we're going to kind of fill in back here, right? And in some way, that's going to give us a formula for the area of one of these triangular cross sections at a given x value. And then we let that slide from 0 to 2. Okay? So really the first integral is filling up this one, getting you a formula, and then the second one is we're pulling it back down this way. Okay? And that's kind of like the meaning of what we're doing here. And when we get this, this is an area function, then we're going to add up those areas to get a volume. Okay, and if you had more questions about this, I could draw you more pictures. Just come and talk to me. And then the last thing I need to tell you is just one more definition. We talked about average value in AP Calculus, and we can still talk about average value. An average is something that's very useful, right? It gives you kind of an idea of a whole data set or something, and you know what you use an average for. Okay? And you also know how to compute it. It is not going to be any different. In elementary school, you found an average by adding them all up and dividing, right? And then in AP Calculus, you added them all up and then divided, but adding them up, it was, integrating and dividing was divided by width. Now, we're going to be integrating over some sort of region, which doesn't really have a width, right, or one-dimensional measure. It needs a two-dimensional measure. So what we're going to do is we're going to define the average value of a function of two variables to be the double integral, and then we're going to divide by the area of the region. Okay. So it's going to be the double integral over R of f of x and y dA divided by, kind of like scaled down by the area of R. And I believe that that's all I've got to show you for this video. In later videos, I'm going to come back with more complicated examples, other techniques that we can use to compute double integrals. And maybe just a video of just me practicing the techniques. But for now, this is what you need to know about volume.